Hi, in this video we will take a look at a RF isolator. I will do a few measurements illustrating how a typical RF isolator works, and later on I will take one apart and take a look at its construction. So a RF isolator is just a two-port device. When the RF signal passes in from its input, let's say here, to the output, we see very little insertion loss, and when the signal direction is reversed, for example, the signal now passes from this end, trying to exit from here, we will get a significant attenuation. RF signals are just a special case of a RF circulator with a matched termination, typically 50 ohm, and this one is actually, you can see here, so that on the third port. So when the signal is reversed, the signal actually gets circulated to this load. So let's take a look at how, on paper, how that works. So basically, we can think of a circulator as a three-port device, port 1, 2, and 3. So when the RF is entered from port 1, then it gets circulated exit from port 2. And if the signal is coming in from port 2, it circulates to port 3. And in similar fashion, if a signal is coming in from port 3, it gets circulated back to port 1. So as for our isolator here, because one of the port is terminated, so let's say port 2 is terminated, and if we take port 3 as our input, input port, and port 1 as our output port, we can see that any signal coming in from port 3 is going to the output port without any attenuation, without much attenuation. Whereas if you wanted to put in the signal from the output port, then you're going to be circulated to this port 2, but in this case, the port 2 is our load. So it will get absorbed by this matched, typically 50 ohm impedance load here, and we'll see very little attenuation, very little signal from the output. So that's in general how RF isolator works. And as the name suggests, it's typically used to isolate the load from the source, so the changes in the load does not affect that of the source. So typically, if you have a RF, well, if you have an oscillator, for example, outputting some signal from the source, you don't want the load to affect that oscillator. For example, you could detune the oscillator if the load does not match the source, and that's where you wanted to use this kind of RF isolator in between. So this specific Harris RF isolator I have here has a passband of between 8 to 10 gigahertz and a rated insertion loss of greater than 20 decibels. So which means, if we put a signal in reverse, we'll see a 20 dB attenuation. Before I take it apart, let's first take a look at its performance. Okay, so now I turned on my noisy HP 8560B spectral analyzer, and up there you will see this the WaveTech 07 microwave signal generator. So that generator can generate signal from 7 gigahertz to 11 gigahertz, which doesn't quite cover the performance characteristics of the isolator I'm gonna test, but it's good enough, and that's what we got here. And so now let me put the input. Actually, for this particular isolator, the input is at the bottom. Let me just put it on. It's not that critical to. Okay, so let me put it here, and the output, we want to put it to the spectral analyzer. Okay, So hang on, this is not very okay. So now, once that is done, we'll take a look at the spectral analyzer, and you'll see the tone there. So what I'm going to do is reset the range to, let's say, between 6.5 and 11.5 gigahertz. So let me come here to say the start range, 6.5 gigahertz, and the stop at 11.5 gigahertz. Okay. So now that gives us a nice and smaller range to look at. And since we're not going to do any quantitative measurement, we're just going to see approximate. So the actual output power really doesn't really matter. And as you can see, we just want to see, the rough shape, roughly what the shape looks like between the input and output. So now, as you can see that we have a tone right sitting at around 7 gigahertz. So it was here. So now let me adjust the output from the signal generator, and which you cannot see is up here. And you should see this peak moves across the screen, staying at relatively the same power, which right now you can see is just below 10 dBm. Just below minus 10 dBm. Okay, so now I'm starting moving, and you can see this peak moves across the screen here. And right now I'm at I'm at 11 gigahertz, and you can see it's relatively flat. So now let me here we go. Disconnect this, okay, and connect the input to the output. So now this one goes directly to the spectral analyzer. That's the input of this isolator. So now let me put a signal from its output. We'll see the performance again. Okay. So now, as you can see from the screen here, this one went down from minus 10 to minus 30, so which is about 20 dBm. So now, if I started turning this backwards, you will see that at some point, roughly here around 9 gigahertz, this return loss dropped to about minus 30 dBm. So which means the curve is not as flat as the forward isolation. Sorry, as a forward insertion loss. So basically, it started as minus 20 dBm, and it dropped to minus 30 dBm, and now it's like minus 35 dBm. At around 9 gigahertz. So that's the sweet spot of this isolator. Basically, it's between, I think it rated between 8 and 10 gigahertz, and you can see at the 9 gigahertz it reaches its minimum. And then as we started tuning backwards, and it gradually starts creeping up. So in fact, we are at now we're outside its operating curve, and as you can see right now, when we're sitting at 7 gigahertz, the attenuation is only about like 10 dBm or somewhere in that neighborhood, as the original signal was sitting at minus 10. Right now it's just below minus 20. So anyway, so that's how this particular RF circulator behaves. And now let's proceed taking it apart and see what's inside. So keep in mind that these are actually precision devices. They're not meant to be taken apart. Of course, every time you take it apart, it will affect its performance. But here we're just going to sacrifice this little isolator, and so we can see what is inside. And that's why RF isolators, those microwave devices, sometimes you can see they're very expensive, because each one of these had to be hand tuned after they're manufactured. So So that's why the cost it's very, it can cost like you hundreds of dollars when purchased new. It's because each individual one has to be uniquely characterized. Anyway, let's take a look. First is this. Sometimes it's glued together. Oh, here we go. So this is our the load resistor. You can probably see this. This has a ring inside, so I would imagine that that's the 50 ohm load right there. So later we'll take a measurement, but right now we'll put it aside and we'll see the other parts. So now let me start taking the BNC, not the BNC, the connector, the SMA connector off. Okay. So as you can see that this SMA connector basically it just there's a tiny slot, so you basically just plugged in right into this little tab here. Okay, so that's the that's one of its terminals, and let's move on to take off. Okay, so this one came up rather easily, and so similar to the other one that we took off, this one is also, if you can see here, there's also a tiny slot where it's made it to this tab here, and so here is our 50 ohm resistance contact. So let's take a measurement of that first. So here I got my meter. Let's set to ohm. Yeah. So let's just see if we can see anything here. So no. Yep, here we go. So you see that it's a 50 ohm. It's a little bit hard to probe this thing. It's a precision 50 ohm termination, as you can see. Okay, so let's move on to try to see if we can take the rest of this further apart, and to see, I can already see some features here. The layers, like there are two discs that is there's a tiny piece of material sandwiched between the two discs. So how the RF isolator typically works is there's a magnet creating a magnetic field across some ferrite material, and so I would expect we'll see some of that. So let me try to open this further apart and we'll take a look. So unfortunately I don't think there's any way that I can open this up non-destructively, so I kind of pried it open, and I realized that the reason I couldn't take it out is because it was glued on at the bottom. So anyway, so now after I kind of cut that open, well, kind of pried it open, I can take this out. Ta-da! As you can see that we have two magnets here. Oh, that's quite nice. So one magnet is on the top and one magnet is at the bottom. Okay, so at the bottom. So the spacing of these actually controls how strong the magnetic field is, and which in turn controls the isolation characteristics of these of the isolator. So actually we can take a look to see if that still works after we take that apart. Let's I forgot which one is which now, which side is which, but it doesn't matter, I suppose. So this is how it was. hooked up before. So let's take a look to see if we can still get that to work. Unfortunately, after I took it apart, it's actually very difficult to get it to work. I was hoping that I could somehow get it to work. As you can see on the spectrum analyzer, now I'm just centered it at the 9 gigahertz. I was hoping that after playing around, I could somehow cause it to change the magnitude, but I can see some effects while I'm changing the magnet, but because everything is falling apart here, it's very difficult to produce a stable signal. So right now you see it's basically, let me zoom in a little bit. This is in its forward configuration, and backward configuration, so isolation mode. Right now I put the 50 ohm termination on, and if I took it off, what happened is all the signals are reflected back to the port. So you will see that the signal, the attenuation is basically gone. Now I put this 50 ohm back very carefully. Yeah, it's very touchy here. Because if I put it just right, you should see that the signal goes down. Unfortunately, this is very difficult to manipulate when it's outside its chassis. So now I don't think I can get it back. Oh, so you see just there. Okay, so if I press really hard, and you can see that the isolation is there. Now what happened is if I take the magnet out, I should be able to see some change. Yep. So now you can see that. Whoops! I took the magnet out. Okay, and now you'll see that the isolation changed. So if I just put the magnet down gradually, I'm not sure if you can observe that. You'll see that the actual reading of the isolation. So anyway, so let me show you what I'm doing here to cause that to the isolation level to change. Basically, you see here, I have to hold it tight because it's just not very stable here. But anyway, so I can use this screwdriver to lift the magnet. So while I'm doing that, that's when you saw the spectrum analyzer signal changes. Okay. And so I just turned off the spectrum analyzer, and we don't need that anymore. So let me actually take this apart. I suspect that like every single one of these, the technician has to tune it by adjusting the screws, adjusting the spacing between the magnets and the fields very carefully in order to get the desired characteristics. So let's take this one out too, and let's take it further apart. There. So now I just took the whole thing apart, and everything again is glued inside, so that I suppose it's to prevent it from moving around. So let's move that away, and you will see that. So this is the core of the RF isolator. So at one end, so this end is where the load was attached. So attached like here, like that. and on either side of this wing is where the not BNC, I kept saying it's BNC, but the SMA connectors are attached. Okay, and on top of and the bottom of this disc, we have this magnet and spacer here. So that creates a magnetic field, and then cause the standing wave in the magnetic field inside this material to behave a certain way that causes the energy to transfer from one port to another. Now, and because solving these Maxwell equations require solving very complex boundary boundary conditions, and typically all the simulations done can only be so much that a lot of the characteristics has to be done during the final testing, and so each individual isolator was tested separately, and that's why these are very expensive. Anyway, so here the inside, this is just the metal piece, basically, and then here are the two ferrite material as we see earlier, and you can see that the inside here, okay, and then this is sandwiched between this two magnetic field, and that's how our RF isolator works. And for RF circulators, it's exactly the same, except the third port here, instead of having this dummy load connection, it will be connected to another connector. Anyway, so I hope you find this teardown very interesting, and if you like the video, please give it a big thumbs up, and I look forward to catching up with you next time.